Hi there, Miss Barber here. This lesson is called Logarithmic Functions. A logarithmic function has many important uses. It is an inverse of the exponential function. The learning objectives of this lesson are 1. Understand logarithmic functions. 2. Be able to graph logarithmic functions. 3. Be able to express a logarithm as an exponent and vice versa. And 4. Know the common and natural logarithmic functions. Roman numeral 1, logarithmic functions. Every exponential function, f of x equals a to the x, with a positive and a not equal to 1 is a one-to-one function by the horizontal line test, and therefore has an inverse function. The inverse function f inverse is called the logarithmic function with base a and is denoted by log subscript a. Formal definition. Let a be a positive number with a not equal to 1. The logarithmic function with base a, denoted log subscript a and read log base a, is log base a of x equals y if and only if a to the y equals x. So, log base a of x is the exponent to which the base a must be raised to give us the value of x. Example 1. Evaluate the following logarithms without using a calculator. A. Log to the base 10 of 10,000 equals. Let's make this algebraic and say that it equals x. Then using the definition, we can rewrite this logarithm as 10 to the x equals 10,000. And we can write this again as 10 to the x equals 10,000 is 10 to the power 4. Since the bases are equal, we can set the exponents equal to each other, and we get that log to the base 10 of 10,000 equals 4. Let's go to B. Log to the base 2 of 64 equals, we'll let it equal some number n. Then rewriting this logarithm as an exponent, we would write this as 2 to the n equals 64. Knowing the powers of 2, we know that 64 is 2 to the 6th. The bases are equal, so we set the exponents equal to each other, and we get n equals 6. So log to the base 2 of 64 equals 6. Let's go to part C. Log to the base 10 of 0.01 equals, we'll just say that equals x. Write this logarithm as an exponent. Then we have 10 to the x equals 0.01. We can rewrite, so let's do 10 to the x equals, and then 0.01 written with a base of 10 would be 10 to the minus 2. The bases are equal, so we can set the exponents equal to each other and get that x equals negative 2. And finally, part D, log to the base 125 of 5 equals some unknown, so we'll write that as to the x. Let's write this in exponential form. So 125 to the x equals 5. This time we're going to do our computations on the left-hand side and rewrite the 125 as 5 cubed to the x equals 5. And then using exponent properties, we could write this as 5 to the 3x equals 5. And let's go ahead and just write to the 1. Since the bases are equal, we can set the exponents equal to each other, and we get 3x equals 1. Solving for x is 1/3. And what this means is 125 raised to the 1/3 will give you 5. Properties of logarithms. The 4 following properties are often referred to as the identity properties of logarithms. First one, log to the base a of 1 equals 0. Its equivalent exponential expression would be a to the 0 equals 1. 2. Log to the base a of a equals 1. The equivalent exponential expression would be a to the power of 1 equals a. Property 3. Log to the base a of a to the x equals x. The equivalent property would be a to the x equals a to the x. And 4. A to the power of log to the base a of x equals x. This is because log base a of x is the power to which a must be raised in order to get x. Roman numeral 2, properties of the graphs of logarithmic functions. Recall that if a one-to-one function f has domain A and range B, then its inverse function f inverse has domain B and range A. That is, the domain and range simply switch. Since the exponential function f of x equals a to the x with a not equal to 1 has domain R and range 0 to infinity, then the inverse of f of x equals a to the x has domain 0 to infinity and range R. The graph of f inverse of x equals log base a of x is obtained by reflecting the graph of f of x equals a to the x along the line y equals x. Consider the logarithmic function y equals log to the base 2 of x. Before we proceed, let's observe that the graph of y equals 2 to the x is provided. And then let's record some points. So if we do x and y equals 2 to the x, some common points. Let's pick -2, -1, 0, 1, 2, and 3 for the x values. Then the corresponding values for the function output, 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. And then let's see, 2 to the 1 is 2, 2 squared is 4, and 2 cubed is 8. Now what we want to do is get the inverse function, and recalling that the logarithm is the inverse of the exponential function, for the log function, what we will do is just switch the domain and range of y equals 2 to the x. That is, we'll take the column that was the function output for y equals 2 to the x and make it domain. So we'll have 1/4, 1/2, 1, 2, 4, and 8. And then for log base 2 of x, that output value will be the domain values for y equals 2 to the x. So we would have corresponding -2, -1, 0. And then for 2, we have 1. For 4, we have 2. And for 8, we have 3. Now let's plot those points. I'll start it at 1, 0, 2, 1, 4, 2, 8, 3. And then going between 0 and 1, at 1/2, we go down to -1, and at 1/4, we go down to -2. Connecting the points, we get the logarithm function, and let's observe that the graph of the inverse function reflects over the line y equals x. Why is that? Because we switched the domain and range. Roman numeral 2, properties of the graphs of logarithmic functions. The domain is 0 to infinity, and the range is the set of real numbers. The line x equals 0, which is the y-axis, is an asymptote. The point 1, 0 is on the graph, and the point a, 1 is on the graph. For example, if you graph y equals log to the base 2 of x, then 2, 1 is on the graph. Sketch the graph of the function f of x equals log base 3 of x. To get started, I might be inclined to find points for y equals 3 to the x, which is the inverse function. And if I were to make a table of values using a t-chart, let's choose -2, -1, 0, 1, 2, and 3 for the x values. Then we do 3 to the -2, which would be 1/9. 3 to the -1 is 1/3. 3 to the 0 is 1. 3 to the power of 1 is 3. 3 squared is 9. And 3 cubed is 27. I will use that to invert the row that switched the x and y to get my coordinate points for y equals log base 3 of x. So this time when I make the t-chart, we'll just switch the x and y columns. We'll have 1/9 corresponds to -2. 1/3 corresponds to -1. 1, 0. 3, 1. 9, 2. I'll go ahead and write 27, 3 as another ordered pair, but that's way off my charts. So let's plot the easier ones to see. I'll start with 1, 0, then 3, 1, then 9, 2. Then I'll just go to, let's see, 1/9 is -2. I can probably eyeball 1/3 a little bit better and connect the points. And here is the graph of f of x equals log base 3 of x. Roman numeral 3, the common log. The logarithm with base 10 is called the common log and is denoted by log x equals log to the base 10 of x. We write it as log x. Roman numeral 4, the natural log. The logarithm with base e is called the natural logarithm and is denoted by ln of x equals log to the base e of x. We just write it ln of x. The natural logarithmic function y equals ln of x is the inverse function of the natural exponential function y equals e to the x. Properties of the natural logarithm are 1. ln of 1 equals 0. 2. ln of e to the x equals x. 3. ln of e equals 1. And 4. e to the power of ln of x equals x. Find the domain of the following functions. A. G of x equals log base 5 of 9 minus 3x. The domain of the log function must be strictly positive. The domain is not defined for 0 and less numbers. So we begin with the argument 9 minus 3x must be strictly greater than 0. Solving, we would get 9 is strictly greater than 3x. Divide by 3 on both sides, so I get 3 is strictly greater than x. It is helpful for me to always have the x listed first, so that's the same thing as x is less than 3, and in interval notation, that would be -infinity to 3. We do not include the 3. Part B. H of x equals the square root of x minus 2 minus the natural log of 10 minus x. So we have two domains with which to contend. Let's start with the square root. In dealing with real numbers, under the square root, x minus 2 must be equal to or greater than 0. So solving for this inequality, I get x is equal to or greater than 2. For fun, I'm going to go ahead and mark that on a number line. So if I mark 2, the equal to or tells me it is solid and x is anything to the right. Now let's look at the logarithm. The argument is 10 minus x, and the requirement for the domain is that it has to be strictly positive. So let's solve for the x, and we get that 10 is greater than x. Okay. Again, I prefer to see my x's first. I'm going to write this as x is less than 10. So I'll mark 10 on the number line, but I'll use an open circle to indicate that it is not included, and x is all to the left. Now, we must have the most restrictive domain, and so that's where both of the lines occur, and it appears to occur between 2 and 10, where 2 is included and 10 is not.